Hello everybody and welcome to Module 13. Now we're into a different section of the course that, believe it or not, is actually testing on means. The name is Analysis of Variance, and that's the nature of the methodology that we're going to employ to perform the tests. But now we're going to be getting into how to test across multiple population means. So again, this is somewhat of an extension of what we've already looked at in Module 10, where we were looking at how to do tests on 2 population means. Well, now we extend that to 3 or more. So just like in Module 12, we were looking at how to perform multi-population tests on proportions. Well, here we are, multi-population tests on means. The multi-population test on proportions were performed as an upper tail chi-squared test. These tests on multi-population means are actually going to be an upper tail F test. So remember back from Module 11 is where we first introduced the chi-square test and the F test. So I'm going to give hopefully a brief explanation of just how this works. So here's our null hypotheses. I'm going to focus on, in this discussion, a test where we have just 3 population means. This methodology will work if we have 4, 5, 6, 10, 20, however many population means we want. I'm just going to focus on 3 because that makes it a little bit easier. So here's my null. All 3 means are the same. Our alternative, this is going to be very similar to what we looked at in multi-population proportion testing, where here it's simply not all are equal. Or you could say at least one is different. So how do we perform these tests? Well, think about how we might have our sample data. In chapter 10, we had 2 samples and we calculated those sample means. So here we had however many observations. I had an X bar 1 and an X bar 2, and we did a t-test or a z-test for 2 populations. Well, now we have a 3rd sample that gives rise here to X bar 3. And again, 4, 5, 6, 20, it doesn't make a difference. It just makes it more calculations. So in this exercise, like all of the other exercises that we've done, the methodology that is employed is where we assume that the null hypothesis is true until we have evidence to show otherwise. So if that's the case, I'm just going to write that we have some common population mean. Again, I'm not writing a 4th sample here. I'm not writing a 4th population. I'm simply saying that if mu1 is equal to mu2 is equal to mu3, they're all equal to mu. I don't need those subscripts. So what I need for this test that we're going to do is a point estimate of what that true common unknown population mean is, under the assumption that the null is true and all of these samples come from one distribution with population mean mu. What is my best guess of that population mean mu? Well, turns out it's what we call X double bar, or the grand mean. And that is just the mean of that entire data set. In other words, we treat it as though those 3 samples all came from the same distribution. So we use all those 3 samples to calculate that grand mean. Now, once we have that, here's kind of a graphical illustration of how this test is going to work. So here's what this might look like if, let me just make this clear, this is if HO is true. If the null hypothesis is true, then all of those samples come from the same distribution. So I have then one distribution, looks something like this. This has some distribution x sigma x bar, which we know is sigma over root n. This has some common population mean mu. And from here, I draw my 3 samples. And again, this is under the assumption that the null hypothesis is true. So let's say here is x bar 2, here's x bar 1, here's x bar 3, no particular order. There's our 3 sample means coming from that one distribution. Now, if they all came from that one distribution, well, what would my grand mean look like? So where would this be? Well, we'll get into the calculations for grand mean in the later videos, but it's going to be roughly an average of those 3 sample means. It is reliant on sample size, but an approximate average of those 3 sample means. So let's say my grand mean somewhere here. Okay, now what if the alternative is true? And for the sake of illustration, I'm going to show this as though they are all different. Again, this is similar to the Module 12 exercise on multi-population proportions. We're testing to see that at least one of them is different. Maybe all of them are different, and that's what I'm going to use for my example here. But the nature of the test is really just to see if one is different. And then, again, if we reject the null hypotheses and we have evidence to support the alternative, at least one is different, well, then we'll have another procedure to identify where the difference exists. We'll get there in later videos. So what I'm drawing in my example is kind of the extreme case. HA is true, very true. All 3 of them are different in this example, which means I really would have then 3 distributions, and I'm just going to try to squeeze them into the space that I have here. So here I have my 3 distributions, and I have, let's say here is mu2, mu3, mu1. X bar 2 came from this distribution, x bar 3 came from this distribution, x bar 1 came from this distribution. Now, once more, where would that grand mean be? Again, that grand mean is calculated under the assumption the null is true, but we don't know if it is or not yet. If the alternative is true, where would my grand mean lie? Well, again, it's an approximate average of my sample means. It will be reliant on sample size, but we'll talk more about that in a later video. So my grand mean may be somewhere here. Okay, so we have these 2 possible outcomes. The null is true or the alternative is true. Now, what we're going to be doing in this exercise, in this module, are estimating different estimates. We're going to be calculating different estimates of the population variance sigma. So we're going to be looking at 2 different estimates of sigma. One of them is what we call the sum of squares due to treatment. And that is based on the difference between individual sample means and the grand mean multiplied by n, that's just the individual sample size, and we add those together across all of our samples. Now, this calculation, it's extremely helpful if we recognize how this calculation is impacted by whether the null is true or the alternative is true. I can see in a world where the null hypothesis is true that these differences between my x bars, my sample means, and that grand mean, those differences are fairly small compared to these differences, except for this one. But in a world where the alternative is true, those differences between sample means and grand means are large. So, SSTR, sum of squares due to treatment, calculates is a component of the calculation of population variance based on the variation between treatments. This is sometimes called the between treatment source of variation. When we divide SSTR by its degrees of freedom, which is going to be k minus 1, where k is the number of samples that we have, this is MSTR, mean square due to treatments. This is, of course, a chi-squared variable with k minus 1 degrees of freedom. So this is one estimate of sigma, one estimate of the unknown population variance. It is based on the difference between sample means and the grand mean, what is called the between treatment source of variation, or between sample source of variation. If the alternative is true, those differences are large, and we say it is an inflated estimate of the unknown population variance sigma. If the null is true, well then those differences will be smaller. And so it is a more accurate estimate of the population variance. So SSTR is entirely influenced by if the alternative is true or if the null is true. If the null is true, SSTR is small. If the alternative is true, SSTR is inflated. It's much larger. Okay? The next estimate of variance is based on what is called SSE. SSE is sum of squares due to error. And SSE is a relatively straightforward calculation. It's based on sample sizes, and it's based on individual sample variance, SI. And we add those up across each of those treatments, or each of those samples. Now, this sample variance, of course, we recognize that that is just calculated as the difference between individual observations, individual observations and the respective sample mean. Now, when we're calculating that variance, this is divided by its degrees of freedom, which is n minus 1. So, those sample variances are based on the difference between individual observations and the individual sample mean. When we divide it by this n minus 1, but then here we're multiplying it by n minus 1, so those effectively cancel out. So what SSE essentially is only those differences between individual observations and their specific sample mean. All this to say, SSE is uninfluenced. It is unaffected by whether the null is true or the alternative is true. It is, when we divide it by its degrees of freedom, it is an unbiased estimate of the unknown population variance sigma. This is NT minus K, where NT is the total number of observations. So in my case of having 3 samples, it would be N1 plus N2 plus N3. K is the number of samples. So in my example here, K is 3. So we have MSTR, one estimate of variance. However, that estimate of variance is entirely influenced of whether or not the null is true or the alternative is true. We have the mean squared error, which is a second estimate of variance, which is unaffected by whether the null is true or the alternative is true. Well, MSE is a chi-squared variable with NT minus K degrees of freedom. What do we have here? I have 2 chi-squared variables. I have 2 estimates of variance. What do we want to do? I want to determine whether or not MSTR is significantly greater than MSE. So this becomes an upper tail F test. because the only reason why MSTR will be greater than MSE is if it's inflated. What makes it inflated? MSTR is only inflated when these differences are significantly large. If those differences are significantly large, well, that only happens if the alternative is true. So that is what we're going to be doing throughout Module 13. We have 3 different types of tests. There's a completely randomized ANOVA, there's a randomized block ANOVA, which is similar to the matched sample design from Module 10, and then there's a factorial, which is a little bit more complicated. We'll discuss that in more depth when we get there. But all of those different types of tests are all based on this same principle. We'll have MSE, this unbiased estimate of the population variance. We'll have MSTR, this estimate of the population variance, which is completely influenced by whether the null is true or the alternative is true, because it's reliant on those distances between sample means and the grand mean. Our test will always be an upper tail F test, because we are essentially testing to determine whether or not we have evidence to show that MSTR is greater than MSE. Because the only reason why MSTR would be greater than MSE is if it is inflated. It is only inflated when these differences are large, and those differences are large only when the alternative is true. So having that F test with MSTR in the numerator makes this an upper tail test. Is MSTR significantly greater than MSE? Okay, that's ANOVA. That's multi-population tests on means in a nutshell. Let's get started on some examples. Thank you all for watching.